I plus 1 minus di. Change in length of this bar is simply displacement of node I plus 1 minus di. Therefore, T is AE over L di plus 1 minus di. That's what we wanted to achieve. We wanted to relate force T to displacement at nodes, and that's what we did. We can write it as it is T is AE over L. This is delta L. Now, compare this one, AE over L times delta L, to a force from a spring. Remember, from statics, we had this spring formula. It is F is equal to K delta L. Previously, we were saying F is equal to Kx, or F is equal to T. In this case, it is K delta L. Now, this is for a spring, K delta L. Now, if you compare for this bar that we were talking about, it was AE over L times delta L. And for a spring, compare this to this. AE over L delta L. This delta L is the same as this one. It means what? It means K is equal to AE over L. Am I right? Yes, K was called what? Remember from our spring formula, K was called spring stiffness. K was called spring stiffness, and it is anyone remembers the units for K? What was the units for K?
Force over
displacement.
Yeah, over displacement.
Displacement, very good, you're right. K, force divided by unit of length. For example, in US customary system of units, it is pound per inch. So now our bar, we end up with AE over L times delta L, and it is for a spring, it is K delta L. So K is AE over L. The units for K spring stiffness, it is as a pound per inch. Can you tell me, you have your paper and pencil, write it down, write AE over L. What is the units for AE over L? Put the units for A and E and L. Tell me what do we get from AE over L? You use US customary system of units for AE over L. Write it down. Tell me what you get for AE over L.
Yeah, force over distance.
Anyone else agrees with your friend or not?
Yeah, force over displacement.
Yep, agreed. Same thing.
Okay, yes, you're right. Look at this one. It is units of K is pound per inch, as what you said, but units AE over L, area is inches squared, E is modulus of elasticity, pound per inch squared, and length is inch. So simplify this, you get pound per inch, the same as K. So what it means that this bar behaves like a spring. Its unit is AE over L. This is behaving like a spring. But the only thing is that since modulus of elasticity is usually a large number, for example, for steel, it is 30 times 10 to the power 6 pound per inch squared, about 200 megapascal. So this is a large number, which makes K to be a large number for this bar. But it is basically acts like a spring with a large spring stiffness, but the behavior is the same. In experimental mechanics, sometimes we use Moret techniques, or we have very sensitive techniques that even with a very thick bar, we just even touch it by a finger and we see that these fringes move, which means that exactly like a spring that it displaces, it deforms like a spring. But this spring is different, it's just large because of E. But the behavior is the same. So we treat it as a spring. As mechanical engineers, actually, you see these structures that actually these springs which are connected to each other because all of them deform them like this. It brings us to our next discussion, which is spring analogy. If I start this discussion, it will be, I don't want to continue because then I have to solve an example problem and we cannot finish this today, which makes me stop our discussion, our lecture at this point. I will not cover any more new material. Any questions so far from what we have discussed? No questions. Okay. What we are going to do, we will continue this discussion next week. We are going to use a spring analogy, treat it as a spring, and write the formulas for this, and then derive the element stiffness matrix for a spring element, and then solve an example problem and review matrix algebra on Monday next week. So that would be our plan for next week lecture. In the lab, you are going to, we will see that everything depends on matrices. So we are going to review matrix algebra. We are going to, you had it in your Math 224. We are going to review addition, subtraction, multiplication, inverse of a matrix by row reduction method. And then the following week, we will talk about simultaneous linear equations, solution of simultaneous linear equations. Then we will learn how to use FEMAP and Nastran to solve our problems. So that is our plan for next week. For this week on Wednesday at 10 o'clock, we will, you again go to Canvas. This course is activated now. Here it is. This is the course. It is active now. You can see this, and we will discuss the syllabus and also the activities we start on Wednesday. All right, if no more questions, I will see all of you on Wednesday to review the syllabus for the activity and also review some metrics.
Professor, do we have to download any software before Wednesday, or would that be covered on Wednesday?
You don't need any software for Wednesday, no. But for FEMAP and Nastran later, in about 2 weeks, I will tell you to download FEMAP and Nastran on your computer so you can have it and use FEMAP and Nastran, but not for this week and next week, no.
And at that point, you'll give it the instructions on how to get it through our engineering.
That's right. I will send you the link and where to get this, FEMAP and Nastran. Yes.
Awesome. Thank you.
All right, sure. Any other questions? All right, if no question, then I'll stop here, everyone. Have a good rest of the day. I will see all of you on Wednesday for our activity. Take care, everyone.
You too.
Thank you, Professor.
Bye. Thank you.